Okay. So we have seen non-homogeneous second order partial differential equations, and what we said is that you can solve them if you know a homogeneous, if you know the solution of the homogeneous equation and a particular solution. Okay. So, suppose you have a non-homogeneous second order differential equation. Is second order and linear ODE. So, suppose you have this of the form y double prime plus a of x y prime plus b of x y equal to c of x. So, if c of x is 0, it becomes a homogeneous differential equation. If c of x is not equal to 0, then it becomes a non-homogeneous second order linear differential equation. Now, if you had such an ODE, okay, now suppose you knew y h of x is equal to c 1 y 1 of x. In other words, y 1 of x and y 2 of x are the basis solutions of the homogeneous equations. Homogeneous equation is y double prime plus a x y prime plus b x y equal to 0. So, for the homogeneous equation y 1 and y 2 are two linearly independent solutions. Okay. So, y 1 and y 2 are two linearly independent solutions of this a x y prime plus b of x y equal to 0. Okay. So, y 1 and y 2 are two linearly independent solutions of this homogeneous equation, and so the general solution of the homogeneous equation can be written in this form. Okay. Now, if y 1 and y 2 are known, okay, then you can find a general solution for this equation, okay, and you can use it by a method called variation of parameters. So, you try y of x u of x y 1 of x plus v of x y 2 of x, where u and v are some functions of x. Okay. So, what you can do is in order to find the solution of the non-homogeneous differential equation, you use the homogeneous equation solutions and you assume that there are some functions u and v which you can multiply y 1 and which you can multiply y 2. So, if you have such a form of trial solution, then what you can do is you can show that I will just write for simplicity, I will not show the dependence on x. So, I will write y prime is equal to u y 1 prime. So, if I take the derivative with respect to x, so I take derivative of this, then I take u prime y 1. Okay. So, this is the product rule for differentiation. Here I take v y 2 prime plus u v prime y 2. Okay. So, this is the first derivative, and then if you take the second derivative, u y 1 double prime plus u prime y 1 prime plus u prime y 1 prime plus u double prime y 1 plus v y 2 double prime v prime y 2 prime plus v prime y 2 prime plus v double prime y 2. Okay. So, if you take the second derivative, you will get this, and then what you do is you substitute these two in this equation. Okay. When you substitute these two in this equation, then what will happen is that you will get simplification, because y 1 double prime and y 2 double prime satisfy the homogeneous differential equation. So let us go ahead and do that. So when I substitute this form into the non-homogeneous equation, what I will get is u y1 double prime, and I will collect the terms. I will collect the terms that are proportional to u. So I have u y1 double prime, then all these terms are either these two are the same term. So you have 2 u prime y1 prime. So I'll write this separately, 2 u prime y1 prime, and then I have u double prime y1. Okay, so these are the these are the terms that you get here, and then what I'll have is v y2 double prime 2 v prime y2 prime and v double prime y2. Okay, so these are, so I just collected all these terms, I wrote them in this form. It will become clear why I did this. Then I have a of x times y prime. So now again what I write is I collect the terms having u. So I'll write plus u a of x y prime, and then the term involving u prime in this case will be this term plus u prime a of x y1, and then I do not have any terms involving u double prime. Okay. And here I will have v a of x y2 prime plus v prime a of x y2. Okay, so that is what I get from a of x y prime. Then from b of x y I will get two terms. The two terms will just be b of x u y1 x v y2. Okay. So I will just get two terms from this. So it is u y1 and v y2. So I will just get this. Okay. So this whole thing should be equal to c of x. The sum of all these terms should be equal to c of x. Okay. So I have written it this way, and then oh sorry, I'll put this term up here. I'll just put this term plus u b of x y y1. Okay. I'll have u b of x y2. Sorry. Okay. Okay. Or v b of x y2. Okay. Now, if you collect the terms in this form, what you notice is that u is common to all these. Okay, and what you have is y1 double prime plus a of x y1 prime plus b of x y1, and since y1 satisfies this differential equation, that term is exactly equal to 0. Similarly, these three terms have v times y2 double prime plus a of x y2 prime plus b of x y2, and again since y2 satisfies this differential equation, those terms add up to 0. Okay. So what you immediately get out of this argument is that these 6 terms just go away and they add up to 0. Okay. So then what you are left with is this sort of equation, 2 u prime y1 prime plus u prime a of x y1 plus u double prime y1, okay, and then you have plus y2 plus v c of x. So you got it. You got your equation in this form. Okay. So I can collect the terms containing a of x as so these are the terms that contain A of x. Okay. Now, what we will do is we will look for solutions that have this term equal to 0. Okay. So, we look for solutions equal to 0. So, we look for solutions that satisfy this condition. Okay. And if you satisfy this condition, then these two terms will go away. Okay. And what you will be left with is something of this form. Plus y1 equal to 0. Okay. And now, again what you notice is that this is a derivative of u prime. Okay. And if you call u prime as capital U, so what you have is y1, this is what this is the first part, plus, and if you call capital V as V prime, where u equal to u prime, v equal to v prime. Okay. And this should sound very similar to you. Or sorry, this is not equal to 0, this is equal to C of x. So, you have two equations, one is u prime y1 plus v prime y2 equal to 0, or in other words u y1 plus v y2 equal to 0. Okay. The other equation is this equation. Okay. And you can solve these two equations, you can solve these two equations for u and v. Okay. And we'll write the solution. So, once again let me remind you, we started with this non-homogeneous differential equation. Okay. And what we had was the solutions of the corresponding homogeneous equation, which were y1 and y2. Okay. And we took a trial solution of the non-homogeneous equation of the form u y1 plus v y2. And so, what is left is to determine u and v. Okay. So, now we have these two equations, both in terms of u and v, and you can easily solve them and you can write the solution. I won't go through the solution, I will just write the final answer. You will get u is equal to y2 C of x divided by y1 y2 prime minus y2 y1 prime. Okay. And you will get v is equal to y1 C of x divided by y1 prime. Okay. Let me just check and make sure y1 y2 prime minus, yes. Okay. So, so if you rearrange these equations, then you can easily show that this is the solution of these equations. Okay. Now, notice that your solution is in terms of capital U. Okay. And you can easily show that is indeed the case. Okay. So, the point is, what we have is we have solved for capital U and capital V, and then you can easily solve you can easily integrate this. So, u is equal to integral u dx, okay. And if you integrate this, what you will get is integral y to c of x dx divided by, and this quantity y 1 y 2 prime minus y 2 prime y 1 is called the Wronskian w. Okay. So, w is called the Wronskian. Wronskian of y 1 and y 2. Okay. And v is equal to integral y 1 c of x dx divided by w. Okay. And y and remember w is also a function of x. Okay. So, w is also a function of x. So, in this way what we have shown is that if you know the solution of the homogeneous differential equation, then you can solve for the solution of the inhomogeneous differential equation using this method of Wronskians. Okay. Now, one thing I should mention right here is that this method of Wronskians is actually quite general. It can be extended to even to higher order differential equations. So, even if you had a third order differential equation which was homogeneous, okay, and or which was inhomogeneous, but you knew the solution of the homogeneous equations, okay, then you could use a method of Wronskians to solve it. So, this method can be extended to higher order differential equations. Okay. So, you can extend this method to higher order differential equations, and we just make a mention of that. We won't actually see how to, we won't do it explicitly, but you have a form that is very similar to this. Okay. In the higher order differential equations, typically you will have more than two basis solutions. So, your Wronskian will actually be a determinant, of this matrix of involving y and y prime, or y 1 and y 1 y 2 and y 1 prime y 2 prime. Okay. So, now the question arises is the following. So, we know how to go from solution of homogeneous differential equation to solutions of non-homogeneous differential equations, but the question remains, how do you solve a homogeneous differential equation? Okay. Are there general methods to solve homogeneous differential equations? We saw that the method of if you had a homogeneous differential equation with constant coefficients, then we could use trial functions like exponentials and then solve it. Okay. Now, in case you had equations of the Euler-Cauchy form, where you had x square y double prime plus x y prime x y prime plus some constant times y, then you could use x raised to m as a solution. Okay. So, those are very specific cases, but is there a general way to solve second order differential equations? Okay. The other thing I should mention right here is that this method of Wronskians is a very general method of going from a homogeneous to from the solution of homogeneous equations to solutions of non-homogeneous equations. In sometimes since this involves calculating derivatives and doing integrals, it can sometimes become a little tedious. There are other tricks you can use. You can use various trial functions. So, depending on the form of c of x, you can choose various trial functions. So, for example, if c of x is a polynomial, okay, you can choose a polynomial as a trial function and then determine the coefficients of the polynomial. Similarly, if c of x is a trigonometric function, you can choose trial functions that are trigonometric. So, there are some simple thumb rules where instead of going through this method of Wronskians, you can use various trial functions and also solve it. Okay, but I won't mention that. You can read about them in many standard textbooks. Okay. So, then we will move to trying to solve differential equations using some general methods. Okay. So, a general method to solve differential equations is something called the power series method. Okay. And I will illustrate this method by taking an example. Okay. So, before we go to that, I will say some general things about what you do in the power series method. So, in the power series methods, you use a trial solution. The trial solution that you use is y is equal to sum over n equal to 0 to infinity C n x raised to n. Okay. So, this is basically C 0 plus C 1 x plus C 2 x square x cube. So, these are various constants. Okay. C 1, C 2, C 3 etcetera are various constants. So, you essentially assume that you have a series, a power series in x. Okay. Now, this might be an infinite power series, it might be a finite power series. If it is a finite power series, you call it a polynomial. Okay. If it is an infinite power series, you just call it as an infinite series. Okay. So, but you just try in this power series form. Okay. So, if you have something like this, then y prime or the derivative with respect to x will be nothing like you have to do term by term differentiation C n times n x to the n minus 1. Okay. And if you do this, the first term will give me 0 because n equal to 0, I get 0. Okay. So, you have 0 plus C 1 plus 2 C 2 x plus C 3 x square. Okay. So, what you have is you have a power series that starts with C 1. So, here you started with C 0, now you start with C 1. Similarly, if you take y double prime, I can write this as and that will start with first two terms will be 0. Okay, corresponding to n equal to 0 means this term will be 0, n equal to 1 means this term will be 0. So, the first two terms corresponding to n equal to 0 and n equal to 1 are 0. Okay, plus 2 C 2 plus 6 C 3 x plus so on. Okay. So, what we are going to do is to take these start with a trial solution of this form. Okay. That implies that the derivative is given by this series and the second derivative is given by this series, and then we will substitute these back in the differential equation and we will see what conditions we get for these coefficients. Okay. And the conditions on the coefficients will determine the nature of the solutions. Okay. So, let us take a specific example. So, the example we will take is something that you will see in quantum mechanics. So, in your quantum mechanics course you will see the example of this sort of equation. The equation is called the Legendre differential equation. Okay, and it has the form 1 minus x square zero. So, let me just check square minus 2 x y. Okay, and just to be consistent, I will call this is minus and this is plus alpha times alpha plus 1. So, the form of the Legendre differential equation is 1 minus x square y double prime minus 2 x y prime plus equal to 0. Okay. So, the interesting cases are when alpha is an integer, okay. But notice that this is a second order differential equation, it is a linear second order differential equation, okay. But you look at it, if you did not have this 1, if this 1 was not there, then it would look like the Euler-Cauchy equation. So, the solution would be a form of, so x square multiplied y double prime, x multiplying y prime, constant multiplying y. So, the solution would be x raised to alpha would be a solution, okay. But that is not the case, and in this case you really do not know what the solution looks like. So, you try a power series solution. So, now if I take a trial solution of this form and I substitute in this equation, okay, then the first term will become 1 minus x square sum over n equal to 0 to infinity n minus 1 C n x raised to n minus 2. Okay, so, that is this term. So, for y double prime I substituted this minus 2 x sum over n equal to 0 to infinity n C n x raised to n minus 1 plus alpha plus 1 sum over n equal to 0 to infinity C n x raised to n equal to 0. So, all I did was I substituted the form of the second derivative, first derivative and the function and y into this differential equation, and I get this result. Okay, so I get this condition, and now we will expand this out. So, when we expand this out, you will have something of this form, sum over the first term will be n minus 1 C n x raised to n minus 2. The second term n minus 1 C n, and then what you had is an x square multiplying x raised to n minus 2. So, x square multiplying x raised to n minus 2 gives x raised to n. Similarly, what you have here is a twice n C n x raised to n, and finally, the last term will be into 0. Okay. So, we have the condition in this form. Okay. Now, each of these terms is a power series in x, and what I mean is each of these terms has terms of x raised to 0, x raised to 1, x raised to 2, x raised to 3, etc., and each of these terms goes all the way up to infinity. Each of these, again, this has polynomials of x raised to 0, x raised to 1, x raised to 2, all the way up to x to the power infinity. So, each of these are power series. So, in other words, this will look like if I expand this, when n equal to 0, I will get 0 because n equal to 0, n equal to 1 I will also get 0, when n is equal to 2 I will get 2 into 2 minus 1, that is 1 into C n equal to 2 C n 1 C 2 x raised to 0. Okay, then when n equal to 3 I will get 3 into 2, that is 6 C 3 x, and so on. So, I get a power series in x. So, that the powers of x will keep increasing all the way up to infinity. Similarly, for this also I will get I will get terms of various powers of x, and for this and for this. Okay. Now, this solution is valid for the entire domain of validity of the solution. So, it is valid for arbitrary values of x, and therefore, this is where we make the important simplification. So, all terms of a given power of x add up to 0. Okay. So, in other words the right hand side here is 0. Okay. So, the right hand side I can write as 0 plus 0 x plus 0 x square plus 0 x cube plus so on. So, then this term, so now what we do is we do term by term, each of these should add up to 0. Okay. So, let us see how that works. So, let us take this and write it term by term. So, if we were to write these term by term, what we will say is the following: in this I have n equal to 0 to infinity C n x raised to n minus 2. Okay. So, let us look at all terms of order x raised to 0. So, all terms where the power of x is 0. Okay. So, all terms where the power of x is 0. Here the term with power of x 0 will be C 2. Okay. So, C 2. So, in this has only one term where the power of x is 0. Similarly, the power of x will in this case the term with power of x equal to 0 will be n equal to 0, and that term is equal to 0. So, this is 0 times x power 0. In this case, the term with x power 0 will be n equal to 0, n equal to 0, this term is n C n. So, n is 0, so it is 0, and in this case the term with x power 0 is n equal to 0. So, you have C 0. So, you have plus C 0 x power 0. So, if you collect all those terms, you will get C 2 times x power 0 plus alpha plus 1 x power 0 equal to 0, and x power 0 is just 1. So, what you will get is that C 2 is equal to minus alpha plus 1, and I have a C 0, yes, C 0, okay, yes. So, this is alpha plus 1 C 0. So, if I collect this, I will have a C 0 here. So, C 2 is equal to minus alpha plus 1 times C 0. Okay. So, notice that by imposing the fact that all terms of x power 0 have to go to 0, or they have to add up to 0, you got a condition between C 2 and C 0. You got a condition for C 2. So, C 2 depends on C 0 in this form. Okay. Now, terms of power x power 1, let us do this for x power 1, and we will not bother writing x raised to 1 in front of each term. So, the term of power x power 1 is if you have to have x raised to 1, then n has to be equal to 3. So, n equal to 3 means you have C 3 into 2. So, 6 C 3 okay. Then in this case, if you have to have x power 1, then n has to be 1, n has to be 1, your n minus 1 is 0. So, this does not contribute. In this case, n has to be equal to 1. So, you get x raised to 1 C 1. So, you have minus 2 C 1, okay, coming from here, and finally, in this case you have alpha plus 1 C 1. C 1, and this has to be equal to 0. Okay. So, then you collect this, you get C 3 is equal to minus C 1 times 2 minus alpha plus 1, so, or alpha plus 1 minus 2. Okay. Okay, so you have alpha plus 1 minus 2. So, C3 in terms of C1. Okay, so this is the next thing you notice. So, what it gives is a relation between C3 and C1. Okay. Now, if you collect terms of x raised to r, okay, where r is some arbitrary integer greater than 1. So, if I look at terms of terms that are multiples of x raised to r, okay, so I am looking at all terms that contribute to x raised to r. So, if I wanted a term that has x raised to r here, then n has to be equal to r plus 2. Okay. So, then n times n minus 1 is r plus 2, n minus 1 is r plus 1. So, this term will be r plus 2, r plus 1, and n we said is r plus 2. Okay. Minus, now in this case, if I wanted a term of x raised to r, then n has to be equal to r. So, if n is equal to r, this is r minus 1 C r. In this case, n is equal to r, because x raised to r you will get when n is equal to r. So, you will get r C r minus 2 r C r. And in this case, what you will get is alpha plus 1 C r. Equal to 0. Okay. And we can write this out. We can write C r plus 2 is equal to minus C r times. So, what we are left with is r minus 1 plus C r into r minus 1 plus 2 r minus alpha plus 1, this divided by r plus 1 r plus 2. Okay. So, what you get is a relation between C r plus 2 and C r. So, if you know terms of orders, if you know the coefficient of expansion of x raised to r, then you can calculate the coefficient of the r plus 2 of x raised to r plus 2 for any r. Okay. So, this is valid for any r. Okay. So, and we can write this. So, this is r minus 1 plus 2 r. So, I can write this as r plus 1 minus alpha plus 1 divided by r plus 1 r plus 2. Okay. So, notice that we got a relation between C r and C r plus 2. Such a relation is called a recursion relation. Okay. So, what we saw is that we looked at terms of power x power 0, we got something like this. So, notice that 2 is related to C2 is related to C0. When we take x power 1, C3 was related to C1. When you take x power r, C r plus 2 is related to C r. So, this is a general theme of this differential equation solution, that C r plus 2 is related to C r. Okay. So, what do we do with all this? Okay. So, suppose you take C5. Suppose you want to calculate C5. Okay. What you will do is you will write this recursion relation, you will write it in terms of C3 times 5 plus. So, C5. So, r plus 2 is 5. So, r is 3. So, C3. So, and r plus 1 is 3 into 4. minus alpha alpha plus 1 divided by 4 into 5. Okay. So, I wrote C5 in terms of C3. Okay. Then what I do is I will write C3 in terms of C1. Okay. So, then what I will write is I will leave this as it is. And then for C3 I will use this relation. Okay. This is this divided by 6, which is 2 into 3. Okay. So, what I have here is I can absorb the minus sign inside. So, I get 2 minus alpha alpha plus 1. So, 2 is 1 into 2 divided by, it will be 2 into 3. Okay. And this whole thing now will multiply C1. Okay. But notice you cannot go from, you cannot write C1 in terms of anything else, you cannot write C1 in terms of anything else. Okay. So, what we wrote is that C5 is proportional to C1. Okay. So, C5 is proportional to C1. Similarly, C7 you can write in terms of C5 first and then C5 to C3 and then C3 to C1. So, C7 is also proportional to C1. So, in other words, all odd coefficients are proportional to C1. And similarly, all even coefficients are to C0. Okay. So, then you can write your y is equal to sum over n equal to 0 to infinity C n x raised to n. I can write this in this form. I can collect all the even terms. So, all the even terms I can collect, and all the even terms will be proportional to C0. So, I can write C0 into polynomial. Okay. So, even polynomial means it will just contain x raised to 0, x raised to 2 and so on. Okay. And I can write C1 times an odd polynomial. So, that will contain things like x, x cube, x phi, etc. Okay. So, the general solution can be written in this form. It can be written as C0 times a polynomial with only even terms and C1 times a polynomial with only odd terms. Okay. And both these it's I should not call it a polynomial yet, I should call it a power series. I should really say power series, and this should also be a power series. And I am emphasizing this difference because this can go all the way to infinity. So, the number of terms can go all the way to infinity. Okay. So, what we have shown by this argument is that you can write this as in this form. All the even terms are proportional to C0, all the odd terms are proportional to C1, and in terms of C0 you know these constants exactly. Okay. So, you know the values of this term. So, there is no undetermined terms in this. Similarly, there are no undetermined constants in this, and so you know this, only thing is you do not know C0 and C1. Okay. But then that is not a problem, because these two solutions, an odd power series and an even power series, are linearly independent, and so these two solutions are actually basis solutions. Okay. So, either of these will be a valid solution. Okay. So, you have found out the two linearly independent solutions. Okay. So, next what we want to see is we want to actually look at this even power series and this odd power series and analyze what these terms look like.